Hi, everyone. My name is Yunqi. I'm a fourth-year PhD student at The Ohio State University. And this summer, I'm working as a research intern at Stellar Development Foundation. Today, I would like to introduce you to Kadabra, an algorithm that adapts Kademlia for the decentralized web. This paper was originally published in Financial Cryptography and Data Security 2023. And the work was done by me and my PhD advisor, Professor Shailesh Krishnan at The Ohio State University. At the beginning of the new century, we saw a lot of attention on decentralized web and peer-to-peer networks. However, back then, we did not have enough computing resources, and we did not have enough network bandwidth. And then the hype went away for quite a while until recently, as we gained more computing resource and network bandwidth, and also the idea of blockchain has emerged. We saw a bunch of decentralized web applications. And decentralized web has once again grabbed our attention. We have all kinds of applications, including social networks, healthcare, payment system, financial applications, and most importantly for today's topic, we have data storage and retrieval. So in a traditional web, a centralized web, data storage and retrieval is handled by CDN and cloud. CDN stands for Content Delivery Network. And they work similarly. The key difference is that CDN servers are very close to you, while cloud services, their servers are further away from you. Cloud services provide computing resources and also storage. Content Delivery Network, as you have probably guessed from its name, provide content delivery. For example, Disney Plus used a third-party content delivery network. And suppose Fox upload the latest episode of Family Guy today, then it should be equally efficient for you and someone in Japan to retrieve the latest episode thanks to Content Delivery Network. And today we focus on decentralized data storage and retrieval. In decentralized data storage retrieval, they usually rely on a peer-to-peer structure. And anyone in this network can serve as a node, can serve as a server, and data can be stored almost anywhere. Statistics show that we have a bunch of peer-to-peer storage systems, and they are getting more popular these days. We will discuss more about P2P data storage and retrieval, its problems, and how we handle them later in this presentation. So no matter we are talking about decentralized data storage and retrieval or centralized data storage retrieval, the key challenge here is to locate and retrieve the data. Statistics show that 25% of users, they will abandon a website if the loading time is greater than 4 seconds. And personally, for me, if a website is loading forever, I'm just going to close it, unless it's my university login page, in which case I have no other choice. And 46% of users, they will not visit poorly performing website ever again. 1 second in delay would reduce your customer satisfaction by 16%. A term used to describe this is called bounce rate. The bounce rate tells you that the longer time your website is taking, the more customer you're going to lose. As for P2P storage, the thing works the same way. If your P2P storage takes a long time to execute a request, then people is not going to use your P2P storage service. Most P2P storage systems today, they are based on a distributed hash table protocol called Kademlia. And interplanetary file system, IPFS, is an example of such systems. Suppose we have user Alice and Bob, and we have a bunch of P2P nodes. Here in this figure, these nodes are actually interconnected. We ignore the connection for illustration purposes and for clarity. And for every node in this system, you are supposed to connect to some other nodes, and you store them in your routing table for future use. Suppose Alice connects to 3 nodes here, and similarly, Bob connects to 3 nodes. And now Alice says, I would like to share this file with content identifier XYZ. The way it works is that Alice will talk to one of her neighbors, and this neighbor is supposed to have a node ID that is close to this XYZ. And if this is not the closest node to XYZ in this network, then that node will try to talk to someone in their bucket, in their table, and we repeat this process until we find the node that is closest to the content identifier XYZ. Their node ID should be closest to XYZ. And later, Bob said, I would like to get the file with content identifier XYZ. So Bob would repeat this process. He would talk to someone, and that someone will talk to someone until we find this particular node. And this node will tell Bob, hey, I see you want to get this file with content identifier XYZ. You should talk to Alice. So Bob will send a request to Alice, and Alice will share a copy of this file with content identifier XYZ with Bob. So that's a oversimplified version of how IPFS works. And so far, everything seems to work great. However, in a P2P network in general, many factors can affect the routing efficiency of a node. This includes, but not limited to, location of that node and its computing resources and also network bandwidth. The big issue here is that Kademlia's routing table, they are randomly chosen. And suppose here we have Bob again. We mentioned that Bob will need to include some nodes in his routing table. And as we have here in the thought bubble, nodes populate their routing tables randomly. In other words, nodes, they are completely agnostic of the environment they belong to. So just to illustrate why this random node population is such a problem, we have some example as Kademlia queries. And suppose we have a source node in California and a destination node in Texas. Since we populate our routing table randomly, you'll probably need to talk to someone in Tokyo, Japan, and they also populate their routing table randomly, so they'll probably need to talk to someone in London. And that London node will probably need to talk to someone in Sydney, because they also populate their routing table randomly. And finally, the query reaches back to the States and gets to its destination. As we can see here, this zigzag path is very unnecessary, and it creates a lot of overhead for this query. So we just had an example of a zigzag message routing path, and that's not the only issue. In Kademlia, we could also see a path that worked like this. Suppose, again, we have the source node in California, and this time the destination node is actually in Asia, in Singapore. So now you route the message to some node in London, and that node route the message to Singapore. So it's just 2 hops. It looks fine. It looks straight and simple. However, in a P2P permissionless system, anyone can join the network, and you could have a very slow London node. It could be for any reason. Maybe they have a crappy machine, or maybe they don't have good network bandwidth. And for any reason, this London node could be very slow, and this slow London node can slow down your entire query process. So the goal of Kadabra is, our algorithm is to configure routing tables such that the lookup latencies are minimized, and also nodes are secure against all kinds of attacks. So here we have a node, and we know that our routing table is limited. We only have this much memory. So how would I pick nodes? How would I make smart decisions on the node I choose to include in my routing table? Before we delve into the details of Kadabra, let's summarize it. Kadabra is the first effort to accelerate distributed hash table protocols via a data-driven approach. And Kadabra automatically adapts to heterogeneity and dynamism in P2P networks. Our algorithm is motivated by the multi-arm bandit problem. We will explain this later in this presentation. And we use novel exploration-exploitation strategy. Kadabra is completely decentralized, and it's secure against Sybil attacks. From the evaluation perspective, Kadabra achieves between 15 to 50% lower lookup latencies compared to state-of-the-art baseline algorithms. And just to put it in a nutshell, Kadabra algorithm nodes, they measure the lookup latency, and we will utilize the lookup latency to find the most suitable peer configuration for themselves. This is just an oversimplified description. There have been many prior works that focused on speeding up distributed hash table protocol. This includes both Kademlia and other DHT protocols. Some of them focus on location awareness. The most famous papers from this one is probably proximity routing and proximity neighbor selection. In proximity routing, you would populate your routing table like you would normally do in Kademlia protocol. However, when you route messages, you find peers that are closest to you. In proximity neighbor selection, you would populate your routing table by finding the closest peer in the network. And when you route messages, you route messages just like you would normally do with Kademlia. Then we have parallel lookups. In parallel lookups, you send out multiple copies of your request. And since you send out multiple copies of your request, normally one of them will get back sooner than others. And we also have recursive routing. When the Kademlia paper first came out in 2002, the authors focused on iterative routing, in which for every hop, the message initiator has to talk to the nodes on the path. However, with recursive routing, as an initiator node, you don't need to talk to the nodes on your path by yourself. And last but not least, we have caching. In caching, the nodes cache the popular items in the network, and they store them. Since the items are popular, people will look up these items in the future, and you cache them, so it should be more efficient. So the issue with these prior attempts is that they did not completely solve the problem. Some of them are inefficient. Some of them are vulnerable against attacks. And here we have some details about Kademlia DHT as a background, so we can introduce the details of our algorithm. So each node in a Kademlia network is assigned a 128-bit pseudo-random identifier called node ID. This length can be some other number, but most often people use 128-bit. And routing tables in a Kademlia network, they consist of sub-tables called K buckets. The data stored in K buckets include node IDs, node IP addresses, and port information. So here we have a toy example of a Kademlia node. We use a 4-bit pseudo-random identifier as a toy example. And the number of K buckets you have is determined by your node ID length. Here we have a length of 4-bit, so we have 4 K buckets. And the most important thing here is that you can only store nodes that share the I-1 prefix. However, the ith bit must be different with you in the ith K bucket. And let me repeat that with an example. Since your ID is, since the toy example ID is 1101, and for your first K bucket, you can only store nodes that start with a 0. And for your second K bucket, that corresponds to the second bit. Since this is a 1, you can only store nodes that node ID start with 10. And another thing to note is that for your last few K buckets, you won't be able to have key items. As we mentioned earlier, we need to look up content. We need to look up items in a Kademlia distributed hash table. And suppose, again, we start from node 1101. This toy example explains how lookup works. We want to look up item 0101. And we go into the routing table of node 1101. And since the target starts with 0, we go to the first K bucket, and we find the node whose node ID's XOR distance to the target is smallest. That will be node 0110. So we talk to node 0110, and from their K buckets, since the target node has node ID 0101, we go to the third K bucket of node 0110. And fortunately, the target node is actually in the K bucket of node 0110. So we find the target within 2 hops. And we get a response from that target node. As we mentioned earlier, Kadabra is inspired by the multi-arm bandit problem. In Kadabra, we treat the routing table configuration problem as a multi-arm bandit problem. And if you're familiar with reinforcement learning, you should know this figure very well. So in a classic reinforcement learning model, you have the agent, and then you have the environment. The agent does something that affects the environment, and the environment will give you some feedback. And you can repeat this process and repeat the learning process, basically. In Kademlia, it turned out that we can map everything to this classic reinforcement learning model. We have the nodes, which are the agent, and we have the rest of the network, which can be considered the environment. And when you configure your routing table, you're actually doing these actions. You're actually taking these actions. And the actions you take, they will affect the rest of the network, which we consider to be the environment. And the environment will give you the feedback, the reward, which we consider to be the lookup latencies. And in the naive approach, in the classic reinforcement learning example we have here, the issue is that if you map everything in Kadabra to this classic reinforcement learning model, you could have a huge number of P2P nodes, and the action space to be huge. How do you deal with this huge action space? So the answer to that is actually quite straightforward. In Kadabra, each K bucket is treated as a subspace, and we consider subspace as independent problems. And going back to our toy example earlier, we have node ID of 4 bits. That means we have 4 K buckets, and each of them is a subspace, and we treat subspace as independent problem. We focus on them one at a time. So now we have the background. Let's delve into the algorithm of Kadabra. In Kadabra, the K buckets store a list of candidate peers. And note that for this algorithm thing, we are focusing on one particular K bucket. So at the end of an epoch, if the next epoch is exploitation, then the K bucket runs the epoch with current peer configuration or previous peer configuration, depends on which one has better bucket score. And if the next epoch is exploration, the K bucket replaces the worst scored peer with a random peer from the candidate list we just mentioned. And the K bucket keeps track of the bucket score of the current and the previous epoch. And where do we get the peers in the candidate list? When there are queries that either initiated by you or routed through your K bucket is going to store this data pertaining to unseen peers, and you will add them to the candidate list. So at this point, you will probably have 3 questions. Let me answer them before you get a chance to ask me. So what is an epoch? An epoch, in Kadabra, we make decisions. We make decisions after a certain number of queries, and we consider the time between queries, between decisions as an epoch. And also, what is the score? The score basically captures the promptness of receiving a response for a query. If it's a score for a particular peer in your bucket, then it's the promptness of getting a response from that particular peer. If it's a score for a bucket, we call bucket score, then it's basically the sum of the individual score from that entire bucket. And finally, how do you know if next epoch is going to be exploitation or exploration? Here we have a user-defined epsilon parameter. You can set the parameter to determine how frequent you want to explore or you want to exploit an existing peer configuration. And here we use an example to explain how the learning process works in Kadabra. And now remember that we are focusing on one particular node and one particular K bucket of that node. Here we are focusing on the ith K bucket of that node. And remember that an epoch represents a certain number of queries. So suppose we have an initial peer configuration with 4 nodes, A, B, C, and D, and we have a bucket score of 65. It's basically the sum of all the individual peer score. And we know that the next epoch is going to be an exploitation epoch. So after n queries, we have a new bucket score of 68, and we use an existing peer configuration. And then we know that the next epoch is going to be an exploration. So we basically replace one of the worst scored peer within that K bucket. And in this particular case, we are replacing node A with node E from the candidate list. And now it's giving us a bucket score of 72. And our next epoch is going to be an exploitation epoch. So we use one of the existing peer configuration. And for illustration purposes, I'm using the configuration from the previous epoch. So now we have a bucket score of 71. And here our next epoch is, again, an exploration epoch. So we replace one of the worst scored peer, which is node D, and we replace it with someone from the candidate list. So now we get a new bucket score of 78. And again, we have an exploitation epoch. We use one existing peer configuration, and we get a new bucket score. So basically, we repeat this process to learn to find a better peer configuration for your routing table. And we repeat this process to improve the routing efficiency of a node. As for the security, a naive way of sampling peers from the candidate list would be picking peers with smaller round-trip time, just like proximity neighbor selection would do. However, we don't like the naive method because proximity neighbor selection does not work well under certain scenarios. They do not adapt to the heterogeneity in the networks. And proximity neighbor selection is very vulnerable to Sybil attacks. In Kadabra, we have a user-defined security parameter rho. And when you sample peers, the round-trip time between you and that peer must have a round-trip time greater than rho. So the intuition here is that we want to sacrifice a tiny bit of efficiency for a lot more security. If you're if I'm sampling you from my candidate list, if you're fast, then I like you. However, if you are too freaking fast, then I don't like you. As for the evaluation, we have two simulators. On the left, we have a square simulator in which we put 2048 node randomly in a square. And for the right, we have a real-world simulator in which we grab the data from Ethereum node chapter, and we map all the nodes to their real-world locations. As you can see here, most nodes are in North America or they are located in Europe. Some of them are located in Asia Pacific. So the model we used in the evaluation, we focus on recursive routing because it's more popular nowadays. And for a routing path with node V, U, and W, with node V being the initiator, and node U being the intermediary node, W being the destination node, we calculate the round-trip time with this following formula. L of xy is just the latency of forwarding a query from node X to Y, and delta X stands for the latency of uploading value over the internet at node X. And here we have the evaluation result for the square simulator. As you can see on the left figure, Kadabra significantly outperformed proximity routing and Valena Kademlia. In this case, proximity neighbor selection actually outperformed Kadabra. This will no longer be the case in the real-world simulator. And on the right, we have Kadabra running for 10 million lookups. For the first 1,000 lookups, we have them in blue, and for the last 1,000 lookups, we have them in red. So this bar chart shows you Kadabra improved the routing efficiency of all the nodes in the network. And here we have the same result for the different evaluation in the real-world simulator. For the real world, we have Kadabra outperforms all the baseline algorithms, including proximity neighbor selection, because proximity neighbor selection does not consider the dynamism in the network. And you can totally have a node that is performing very well at this time, at time t, and at time t plus delta, this node is not performing well for certain reasons. And again, on the right, we have this bar figure that shows Kadabra improved the routing efficiency of all the nodes as time goes by. So those are the actual lookup paths of the same query for different algorithms. We show them here as an example that explains why Kadabra works well in the routing process. First, we have Valena Kademlia. It's the first baseline algorithm. And in Valena Kademlia, we only have 2 hops. However, the intermediary node can be very inefficient, and it gives you a latency of 24,000. And then we have proximity routing. In proximity routing, you populate your routing table as you would do in Valena Kademlia. When you route messages, you find the node that is closest to you for the current hop. The thing is that you populate your routing table the same way as Valena Kademlia do, and it could be very likely that you include a bad performing node in your routing table. And then we have proximity neighbor selection. In proximity neighbor selection, you populate your routing table first by selecting the peers that are close to you. And when you route messages like you would do in Valena Kademlia. The thing with proximity neighbor selection is that you only focus on your current hop. If your current hop is performing very well, then you choose it. However, you don't care for the future hops of this message. And here comes Kadabra. Kadabra chooses neighbors based on their overall performance, not only for the current hop, but also for future hops. And we also evaluate Kadabra in many other situations. In the presentation, we focused on distributed hash table, but in the experiment, we also did key-based routing. And we also did iterative routing, although we focused on recursive routing. We tried hotspot, in which some resources are more popular than others. And we also have skewed network bandwidth, in which some nodes are slower than others. This is actually very common in the real world we live in. And then we experienced with unstable networks. We introduced a noise parameter to the node latency and see how Kadabra performs in an unstable network. So in a nutshell, our results suggest that Kadabra outperforms all the baseline algorithms in most situations, and it provides better security. And if after this presentation you don't remember anything about Kadabra, I hope you at least get this takeaways. So first, Kadabra is a simple data-driven algorithm for peer-to-peer configuration. And Kadabra adapts to heterogeneity and dynamism in P2P networks. Finally, Kadabra is secure against common attacks. As for future work, we want to test the performance of Kadabra in real-world networks. And we would be happy to see some thorough analysis of Kadabra's robustness against attacks. And last but not least, it'll be interesting to do a better theoretical understanding of Kadabra. We believe this can be done using series from network potential games. And it'll be interesting, specifically, it'll be interesting to analyze the social cost of Kadabra in a local connection game. So this basically means, suppose you have a central controller of the Kademlia network, then you can basically give a optimal peer configuration for every node, and every node has to listen to this central controller. What if you don't have the central controller? You basically have a price of energy in which you want to compare the optimal result you can get from the central controller versus everyone do this in a decentralized way. And that's it. Thank you for your attention. Please check out our papers. For the QR code on the left, we have Kadabra, and for the QR code on the right, we have our recent paper about blockchain data sharding using P2P random walks. And now I would like to take any questions you have.
Okay, thank you. This is a really cool idea, and I'm just being devil's advocate here, but in the real world, does this end up where only, say, like AWS nodes end up being, the data only gets routed through them because they're always going to have the better latency than everybody else, and then like edge nodes operated by people never get routed through?
It depends on many things. So like, it also depends on what things you're looking for. Like people have different interests. Some like there are many popular videos on YouTube, right? But you can have different categories, and it's not like some companies they are gonna take charge of this entire thing. But it depends on what your subfield is. Yeah. So like, we hope there will be big companies, but big companies won't be able to take the entire thing off this Kadabra network.
Yeah. Thank you.
Hi, Pradyum Shum, Flashbots and Georgia Tech. I had a question about censorship resistance. Could you say anything about how this could, prevent some parties from making some content inaccessible?
So like for censorship, are you saying that you can eclipse a node, like block all the information that's coming through that particular node?
Right. If you don't want some pieces of content to be accessible in certain regions or by certain requesters.
Yeah, that's actually the Sybil attack we tested in our simulation. So we have this security parameter that prevents you from being taken by a Sybil group. And I mean, if you're a Sybil group, you want to get into the key buckets of your victim node. However, since we have this security parameter, even if you're performing good, you won't be able to completely take over the routing table of your victim node.
Thank you.
Yeah.
I have a question about, so one of the big problems we found with Kademlia was that it has very poor resistance to Byzantine nodes, so nodes that actively attack the network. Because, for example, it's very hard to detect them because an honest answer can always be, here are more nodes that you can query, and a Byzantine node can simply just always send more Byzantine nodes. Does Kadabra have any resistance to this, and what percentage could it tolerate?
Yeah, that's a very good question. We actually considered this during our experiments. So If you think about malicious nodes, if you think about Byzantine node, what are Byzantine node? If you can help me achieve my goal, are you still a Byzantine node? So if you have a bunch of Byzantine node in this Kadabra network, and you can efficiently help me find my resource, my target, then I don't care if you're a Byzantine node, as long as you can get a response, a good response for me. However, if you cannot get a good response for me within a reasonable amount of time, then you're not a good node. I won't include you in my routing table. So in this paper, like, how do you define Byzantine node is a question. Like, if you can do good things for me, then I don't care if you're a Byzantine or not.
Okay, let's thank the speaker again. We're now on break, and we'll resume